All right, so let's start off kind of a couple of demos here. So we'll take some water, add my favorite indicator, phenolphthalein, and I got that. So then the first one, I've got chunks of calcium, okay? That's a technical term. So it's got kind of like this grayish solid. So I'm gonna react calcium and water. So let's just start with that idea. How would you chemically represent the idea that I'm going to drop a piece of calcium into water? What am I going to write?
Ca plus H2O.
Ca plus
H2O.
H2O, right? Now, here's the deal. This is why you got to put these, this is the solid form of calcium, okay? This is not the calcium ion, okay? It's not bound to anything. It is a chunk of calcium, right? And then I've got liquid water, okay? Later on, you'll see that there's different types of water. You can have water vapor, you can have liquid water, you could have ice, okay? So this is just going to be liquid water. So right away, when I write this, why don't I put, if you look, calcium is in group 2, right? So why don't I put a charge of +2 up there? Parker. Hold, somebody said what?
Chunk of calcium.
Yeah, it's just a chunk of calcium. It hasn't reacted with anything. It has all of its electrons. It hasn't given up electrons. It hasn't taken in electrons. It's just a chunk of calcium, right? So as soon as you see calcium, an element, plus a compound, what's the only type of reaction this is going to be? Single displacement, or some usually call it a redox reaction, right? Redox says, Leo says dirt. Lose electrons, that's oxidized, gain electrons, that's reduced. So something is going to give electrons, something is going to take electrons. Okay, so I'm going to fundamentally get something different, right? So out of this, okay, so the calcium is going to come along, and this is what you've got to be able to think through on the test. So if you look on that pink piece of paper, hold on. I was organized. Somebody give me that redox, that one. Okay? So when you look up here, and this is what you're going to have on the test, okay? Up here, here's calcium. Hydrogen's down here, okay? So that means calcium, and this is going to be important. Calcium as the elemental form of this, and this is going to be important. This is not the ion form of it. This is the metal form of this. Calcium is more reactive than hydrogen is. So it's going to come in, and this is what you're going to have on the test, right? So you got to realize, oh, calcium is more reactive. It's going to kick that out. Now, there's two possible things you could get out of this. You could get calcium oxide and hydrogen gas, or you could get calcium hydroxide and hydrogen gas, or you could get calcium hydroxide and hydrogen gas. Okay? Those are the three things we could get. So, how could we determine, since we put phenolphthalein in here, phenolphthalein turns magenta into basic solution. So how could we determine which one we're going to get? What could we do? What would happen if we produced hydroxides? What would that color change to? Yeah, it would turn magenta. It would look like Addie's sweatshirt. Okay? So I'm going to take this piece of calcium, and I'm going to dump that in there. Okay? And first off, you'll notice that it sank. So what do you know about the density of calcium relative to the density of water? More dense. Okay? Now, I'm getting a lot of bubbles being produced. So that's going to indicate that I'm producing then hydrogen gas. Okay? So the bubbles have got a lot of bubbles forming. Okay? Now, what color is the solution turning?
Blue.
Turning magenta, right? So because of the fact that that thing is turning this magenta color, what are you producing?
Hydroxide.
Hydroxides. So here's the deal. If, got a little crazy there. If we had produced calcium oxide, okay, then it would not have turned that magenta color because there would be no hydroxides present in that reaction. So by virtue of the fact that it turned magenta means that I produced some hydroxides, okay? So that means that's not going to be it, okay? It's not, that did not happen. Now, based upon that reaction, someone at Christmas says, wow, here, I got you a calcium necklace, and it's made out of pure calcium, okay? Made out of pure calcium. Would you want to wear that when you wash dishes?
No,
Why not?
because it reacts with water.
Yeah, it reacts very violently with water, okay? So this is why we don't use calcium in jewelry, because of the fact that it reacts very violently with water. Now, but here's an anomaly. What's one of the main components that make up the bones in your skeleton? Calcium. Wow. Okay? Huh. Calcium makes up your bones. It's odd. You have a lot of water. Everybody's about 10% water. You have a lot of water in your body. So why isn't the calcium that makes up your bones then reacting with water? And if that happened, we wouldn't be here having this discussion.
That's the stop.
Because so what does that mean? Is the calcium that makes up your bones elemental calcium?
No.
No, it's given up its electrons because it's the more stable form. You have calcium, and it used to be, oh, you got to drink milk because milk was a good source of calcium, okay? Oh, it allows you to build stronger bones because of the fact that you're getting calcium from the milk. Because the calcium to build your bones has to come from somewhere, okay? It's like a factory. Oh, hey, I want to produce cars. Okay, cool. What are you going to need to produce cars? Tires. Okay, well, you got to ship the tires into the factory to assemble the cars. So the same thing is true of the calcium that makes up your body. Your body is continuously reinventing itself, okay? You basically don't have any of the same cells that you have probably even when you started this year. You don't have the same blood cells, same skin cells. You are continuously, your body is continuously reinventing cells, okay? And so you have to, it's like a factory. You have to have a fresh supply of those. So when you look at something like this is what you've got to be able to do. Take a simple reaction and go, okay, how can I roll that into a bigger idea? Oh, right, calcium reacts with water. I got calcium in my bones. That means that the calcium that makes up my bones is not the elemental form of calcium. It must be in the more stable form of calcium. Okay, so I have a choice. Do I get calcium OH or do I get CaOH2? Miles.
CaOH. 2.
Why?
If it was just CaOH, it would have.
No.
I don't know.
Calcium. Miles, look at the periodic table. Where's calcium at? Which
Two.
column?
Oh, 2.
So how many valence electrons does it have?
2.
So therefore it has a charge of
2.
plus 2. Emma Hayes, what's the charge on hydroxide?
-1.
So that's why it's going to be CaOH2, right? Peyton Queen, why do I have to put those brackets around there?
Because if you didn't have brackets, it would look like you have 2 hydrogens and just 1 oxygen.
Fantastic. Okay? So here's what I got. I got calcium plus water yielding calcium hydroxide and hydrogen gas. Now, is that balanced? Carter Smith, is that balanced? Not even close. Not even close. Carter Smith, how many hydrogens do I have on the right side?
On the right side?
Yep, on the product side.
4.
4. How many do I have on the reactant side?
2.
Now what am I going to do? Change it to H4O?
No.
No, horrible form. What am I going to do? And what do we call that too? A coefficient or a subscript?
Coefficient.
Beautiful. Now is it balanced?
Yeah.
4 hydrogens, 4 hydrogens. 2 oxygens, 2 oxygens. Life is good. Now, is that my net ionic equation?
No.
No. Okay, now here's the deal. In this case, it actually is. Because this has no spectator ions. Because the calcium goes from elemental calcium into calcium 2+. The water gets split apart. So this is a rare instance where the reaction is the net ionic reaction, because it's the exact same thing. There are no spectator ions. Everything is changing forms, so there are no spectator ions. So that is it. Now, one of the things you got to be able to do is use your solubility rules. So what do you know about hydroxides? Is calcium hydroxide soluble or insoluble? Now, just based upon the fact that this is pretty murky, that might give us an indication of what might happen. So, Miles,
Yep.
what does it say about hydroxides?
It's insoluble.
Why?
It's not on the soluble list.
Yeah, it's not on
Isn't
the soluble list, okay? So if it's not on the soluble list, it's kind of like Santa Claus. If you're not on the naughty list, you're on the good list, okay? So if you're not on the soluble list, you're on the insoluble list, okay? So Santa Chemistry Claus checks his list, see who's soluble or insoluble. It's like, which list do you want to be on? I'm just saying, okay? So calcium hydroxide is on the insoluble list. This is why this looks so murky, is because we have formed a precipitate of calcium hydroxide, okay? Cool with this one? Good. Got it? Okay. Reaction number 2. Take a little bit of phenolphthalein. Ding, ding, ding. Okay. Then I'm going to take elemental lithium. Okay. So I'm going to take a chunk of lithium. I can't grab it with my hand, so I'll stab it.
Oh. Whoa. Yeah, let's not stab each other, okay?
Oh, come on. It's just one big round chunk, and I'm trying to stab. No. Try not to cut my finger. That would help. Usually this is really soft and easy to do.
How is it weird?
But for some reason, okay, if anybody asks, you never saw what I'm about to do.
Because it is. See how little big. And it turns out the parentheses. So it is just.
Okay, what I just did, you all never saw. Okay?
It's using front. It's not so.
All right, so I'm going to take a chunk of lithium. Cut that off. Okay, so now I got a chunk of lithium. So I'm going to react that with the water. So what do you notice about that lithium?
It's turning green. It's turning orange.
Okay?
It's sitting on the top, I think.
So it's
I can't see
floating. So unlike the calcium, the lithium is
it.
less dense than water, right? So what else are you producing out of that? Magenta color, so we're producing hydroxides, right? And we're producing some bubbles, which means we're producing a gas. So we've produced a gas and so you can tell that even like that lithium reacted with a little bit of water on my skin, and I have a little bit of phenolphthalein in it. So that's why my hand looks like I'm turning into a mutant right now.
Oh, don't worry. It's not really a lot.
Turn into Barney, bro.
That's why what I just said, you all saw, never happened. Now, here's the other difference. And this is why I chose these particular reactions. So notice that the reaction between calcium and water produced a very, very murky substance, right? The reaction between lithium and water is very clear. So that means this is producing a precipitate, this is producing a soluble product. That's why this is clear. So, here's the setup. Lithium and water, right? So we could get lithium oxide and hydrogen gas, or we could get lithium hydroxide and hydrogen gas. So, which one did we get? Emma Hayes.
Hydroxide?
Yeah, we got hydroxide because it turned magenta. Okay? It's nice. Now, this one. So I have Li plus H2O is going to have lithium hydroxide and hydrogen gas, right? Look, Etheridge, is this balanced? Really?
No.
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 No. No. No. So what are we going to do to balance it, Luke? How many hydrogens do I have on the right side?
We got 3 on the right and 2 on the left, so we need to put a 2 in front of the water, and then
Okay.
put a 2 in front of the lithium hydroxide, and then put a 2 in front of the lithium.
Oh, how cool is that? It's nice, right? Okay? So now it's balanced. True? Now, here's the deal. Here's the difference. Lithium hydroxide is soluble, okay? Calcium hydroxide is insoluble. So this situation here, now I need to write out this net ionic equation. So because of the fact that that was a chunk of lithium, I'm going to keep that together as lithium. I've got water. Now, here's the difference. I'm going to separate out the lithium hydroxide because lithium is in group 1. It's an alkali metal. All alkali metals are soluble. So this is existing as Li plus OH minus. Now, I'm going to keep the hydrogen gas together because it's hydrogen gas, okay? I don't separate things that are insoluble, and I don't separate gases, okay? I just keep that as hydrogen. Now, here's the deal. Again, it's not balanced. So here's what you're tempted to do. Go, oh, I'll put a 2 there. Now I've got 4 hydrogens. I'm going to come, then 2 oxygens, so I'll put a 2 over there. And now, look at this. Oh, I got 1 lithium. I have 1 lithium. I have 4 hydrogens. I have 4 hydrogens. I have 2 oxygens. I have 2 oxygens. And I'm done. Okay? That's what you're tempted to do. Okay? But don't. Why is that not a correct balanced net ionic equation? What is wrong with that yet? You have to balance charge and you have to balance the number of particles, right? Mm-hmm. So, what's the total charge of everything on the product side?
1 minus.
Yeah, because I got two negative charges and a plus. So over here, that's -1. My left side is 0. So I got to balance this out. So I've got to put a 2 here. Now, my right side has a sum of 0. But now I have 2 lithiums, so now I've got to put a 2 there. Okay? So when you have, and this would be true whether it was sodium, potassium, any alkali metal, and I promise you, if you get down to the test tomorrow and you haven't done a reaction between an alkali metal and water, you have done something horribly wrong. Okay? Actually on Monday. So, I promise you, you are going to have to do a net ionic reaction like this. It's on that lab that I just gave back. Okay, so you make sure that you understand how to do reactions between alkali metals and waters. Okay, promise you, that's going to be there. Now, so in here I have a bunch of lithium hydroxide. So to that, I'm going to begin to add some hydrochloric acid. Okay, so now I'm going to begin to add hydrochloric acid. So, in this, I have lithium hydroxide. That's basically what I have left in there, right? So the lithium hydroxide is going to begin to react with the hydrochloric acid. Now, what type of reaction is this going to be? Grace, what type of reaction is this going to be? I got lithium hydroxide and hydrochloric acid. Single displacement, double displacement, decomposition, combustion, synthesis. What'd you say?
Double.
Beautiful. Okay. Now, here's the deal. Notice that these are everything here is soluble. Group 1, boom. Okay. So this is going to be an aqueous form of hydrochloric acid and an aqueous form of lithium hydroxide. They have to be this way because that's the only way they're free to mingle. Okay. All right? They're free to mingle. If they're locked up, they can't do this. So out of this, what am I going to get? Ramen. What am I going to get out of this?
Out of which one?
Out of this lithium hydroxide and hydrochloric acid reaction.
You're going to get H2O.
We're going to get water.
Lithium chloride.
And what?
Lithium chloride.
Fantastic. Balanced?
Yes.
Yes, it is. Okay, boom, there we go. Is that my net ionic reaction?
No.
No. Now, I promise you got to be able to do this net ionic. Lithium hydroxide soluble. So you're going to write this as Li plus OH minus. Hydrochloric acid, very soluble. That's what makes it a strong acid. Now, am I going to separate the water? Parker?
No.
No, it's the molecular form, right? I'm going to keep that together as H2O. Is lithium chloride soluble or insoluble?
Soluble.
Why?
You just said it was.
Okay, but beyond that, on the test, I'm not going to tell you, hey, by the way, everybody, number 5, lithium chloride, that's soluble, okay? What's the rule on chlorides, bromides, iodides? They're almost all soluble except for silver and lead. Lithium is not either one of those, therefore this is existing as lithium ions and chloride ions. So, what are my spectator ions, Al, girl?
Hydrogen. Wait, no. Chlorine.
Yep,
Lithium.
yep. That's it. So my net ionic is hydrogen plus OH yielding water. That's my net ionic equation. Okay? So if I keep adding this, I might not have enough of this. Okay? So I added it, and now it quit being magenta. Why did it quit being magenta? What happened to all those hydroxide ions? What happened to them? Did they just disappear?
They got broken down.
No, it's just the opposite. What did those hydroxide ions do? They reacted with the hydronium ions to produce water. So the reason that this is no longer clear is because of the fact that the hydroxide ions are there, but now they're just bound up with the water. And so now it's no longer a basic solution, I turn it acidic. But if I add, say, a little bit of sodium hydroxide to it, then I can shift that back to being the basic solution. Come on. The longer it takes to fade out, that's the closer you're getting to it being basic. Oh, come on. It's kind of gross, you can see it swirling around in there. There we go. Okay. All right, so let's talk about that assignment from yesterday. Okay? Let me kind of go over the ones that are missed most. What?
Number 8.
Okay. That actually wasn't one of those that's missed most, but we can talk about number 8. So here's the deal. Now, let's talk about, there's 3 of these in a row. And this is what Mild had asked about earlier. So notice on, there's actually like, there's that magnesium chlorate, there's the aluminum hydroxide one, there's the aluminum one, there's 5 of those in a row. All of those have heat. So what that means is when you're adding heat, it's just like melting ice. If you want to melt ice, you have to add heat. The heat is going in there to break the bonds that hold this substance together. So whenever you see heat on the reactant side, and there's only one thing there, this can only be a decomposition reaction. Okay, that's it. So the heat is just there to break the bonds. That's all it's doing, right? So on number 8, you have sodium oxide. So right away, let's say I write this, sodium oxide. So there's 3 different ways that you could write sodium oxide. Oh, sodium oxide, NaO, there you go. Then you go, oh, oxygen is a diatomic. I'm going to write that as NaO2 because I remember, in my mind, I remember that oxygen is diatomic, so I'm going to put a 2 out there. Or I'm going to go, oh, oxygen is 2 minus, sodium is 1 plus. I'm going to write it as Na2O. So which one's right?
The bottom one.
Bottom one, okay? So if you don't start with that, you're dead in the water right from the get-go. Okay? You're absolutely dead in the water. You've got to start with sodium oxide. Now, if all you have is a binary compound like this, the only thing you can do is split it up. Okay, that's all you can do. So the only thing you can do out of this is just get elemental sodium and oxygen gas. That's the only thing you can do. So if it's just a binary compound, you just split it up. Now, here's what you're going to do wrong. You mark my words, okay? So you're going to have that. Is it balanced?
No.
No. What are you going to have to do?
Put a 2 in front of the left side.
Put a 2 here, then what?
Put a 4 in front of the NA.
Okay? Score. Okay? Think about that one, Robin?
Yes.
Now, but here's what you're going to do wrong. And you all sit there and go, oh, Mr. Burkamp, we won't do that. Yes, you will. Okay? Here's what you're going to do wrong. You're going to go, oh, I'm just going to write that as Na2 plus oxygen. Chemistry isn't tough. Okay? Is sodium diatomic? No. Okay? Train wreck. Or you're going to put Na2O, and then you're just going to write sodium, and then you're just going to put the oxygen. Bad. Why? Oxygen is a diatomic, so you have to put that 2 out there on that one. Okay? Now, let's talk about, for example, number 21. So you have Br2, elemental bromine, plus sodium chloride. Okay? Now, here's the deal. Your halogens are their own reactivity series. Okay? So where's the most reactive halogen? At the top or at the bottom? Top. Most reactive halogen is at the top. So where's bromine in relation to chlorine? Below it. So which one's more reactive, bromine or chlorine? Chlorine is more reactive. So if I put bromine in with sodium chloride, what's going to happen? Absolutely nothing. Okay? Because Mother Nature goes, I'm at the bottom of the energy well, I'm cool. This will get you no reaction. Because Mother Nature goes, it's just not going to happen, because everything is already in its most stable form. So that would not get you reaction. Yes?
How many no reactions are there?
Not very many. So let's talk about, for example, perhaps number 24. Okay? So we're going to take a chunk of silver and we're going to put that in hydrochloric acid. So that would be an example if we were to actually do this. So let's say that I've got a nickel, okay? And I'm going to put a drop of hydrochloric acid on that nickel. When you do that, you'll notice that absolutely nothing happens. Why? Yeah. So if you look at where silver is, okay, if you look on that reactivity series. Where's silver at on that reactivity series? It's below hydrogen, right? Okay? It's below hydrogen. Means it's not going to happen. Okay? So this will get no reaction. Now, however, what if I take a chunk of zinc and react that with hydrochloric acid? Now what's going to happen? It'll react. Why?
Because it's higher than hydrogen on the...
Yeah, so zinc is above hydrogen. So this is going to be a single displacement reaction, or a redox, however you want to call it. And now, what I'm going to write is wrong. Oh, I'm going to get zinc chloride and hydrogen. Okay? It's a train wreck. Why?
Zinc is 2+.
First off, what is the hydrogen? I would produce hydrogen gas, which means I'd have to do what? Put a 2 there. What about the zinc chloride? Why? Beautiful. Zinc is 2+, chlorine is 1-, so that should be ZnCl2. Balance it, I'm going to put a 2 there. Now, if I did this reaction, let's talk about this reaction. And what you can do with a flame. If you were to run this reaction and put a burning wood splint into the test tube, what sound should you get? A pop. Okay? You should get a pop. So there's 3 flame tests that you need to know. 1, if you get the pop, that's an indication of hydrogen gas. The glow test, if you put a glowing splint in and it gets brighter, that's an indication of oxygen. If it goes out, you get carbon dioxide. Okay, so those are the 3 flame tests you need to know going into that test on Monday. Pop goes the hydrogen, glowing, there's an oxygen in there, it glows brighter. If it goes out, the GO, kind of like CO. Goes out, CO, carbon dioxide. Okay? Those are the 3 that you need to know. So, if you look at, say, for example, number 16. So in 16, you dropped a piece of magnesium into sulfuric acid. Sulfuric acid is H2SO4. So right away, what type of reaction is this going to be, Mr. Grill? Single displacement. Okay, you have an element and a compound, right? Mr. Grill, where's magnesium in relation to hydrogen on that reactivity chart.
Isn't it above it?
It is, very much above it. So there's the magnesium going to kick out the hydrogen.
Yes.
Now, in this situation, it actually kicks out both hydrogens. Okay? It isn't like water. Because water, once you get rid of one hydrogen, it actually holds on to that other one pretty tightly. So it's like you're at the zoo and you're babysitting two kids, and one of them, Timmy, gets eaten by the lions. And it was like, oh, it's Timmy, my bad. Okay? So his little brother Tommy, you probably want to guard Tommy a lot better, more tightly, because of the fact that it's like you don't want to go to mom and dad. It's like, well, I lost Timmy, and Tommy. It was a bad day, okay? At least if you hold on to Tommy, you can go, hey, I got one of your kids back. Back off me. I'm batting 500. That'll get me into the Hall of Fame all day long, batting 500. Okay, so, but with sulfuric acid, it actually kicks out both of them, because the sulfate, it isn't very tightly bound at all. This is what we call a strong acid. So you're going to get MgSO4 and hydrogen gas. So why do I write that as MgSO4?
Because that's stable.
Yeah, what's the charge of magnesium?
2 plus,
2 plus. What's the charge of sulfate?
2 minus.
2 minus. Okay? There you go. Let me see. What's another one that's missed a lot? Where's it at? Number 10. 10's a doozy. So let's talk about number 10. So you have calcium hydroxide, okay? Basically this stuff, okay? And you're going to react that with H3PO4, which is phosphoric acid. H3PO4, okay? Now, right away, what type of reaction is going to take place? Keaton. Double displacement, okay? So the calcium is 2 plus, the hydroxide is 1 minus, the phosphate is 3 minus, the hydrogen is 1 plus. So these are going to switch partners, right? So the calcium is going to come over here and it's going to react with the phosphate. So the first thing that you have to be able to do is write the formula for calcium phosphate. So what's going to be the formula for calcium phosphate?
C3.
Ca
PO4 2.
3 PO4 2. Go with that, everybody, because you can't do that. We are dead in the water. Okay, calcium phosphate. Then what are you going to get? How about H3OH? How about that? Bad, horrible, stop, no. Bad. What do you get when hydrogen and oxygen combine? Water. Why water? What'd you say? It's the most stable form. Okay? So you're going to get water. That's it. I think you just have to balance it. Okay? Then you just have to balance it. So this is what we call a neutralization reaction. You have calcium hydroxide. That's a base. It has hydroxides. This is what's known as phosphoric acid. It's called a triprotic acid. It's called triprotic because, oddly enough, there's 3 hydrogens on it. So you have triprotic acids, which is like H3PO4. Those are pretty rare. Then you have diprotic acids, which is H2SO4. Diprotic, oddly enough, means that it has 2 hydrogens. And then you have monoprotic, which is hydrochloric acid. So you have monoprotic acids, HCl, diprotics, H2SO4, triprotics, which is phosphoric acid, H3PO4. So anyway, so if you balance that one correctly, you should end up with 6 waters.
6 waters.
Yep.
Okay.
What's 6 in Spanish? Siete? Ses, yeah. Ses aguas. There you go. That's
Can
it.
you do 18?
No.
Please.
No.
Whoa, why?
Okay.
Whoa, was that adequate? Not big enough.
Just a little bit. 18?
Yes.
So you have C4H10, right? Plus O2. So right away, what type of reaction is this going to be? Yes, you have a hydrocarbon and oxygen. Okay? So what are the beauty of the beauty of combustion reactions is what's the only two products you're ever going to get out of a combustion reaction? Carbon dioxide and water. Now, you get heat, but we don't have to balance heat. Okay? If you take AP chemistry, we do a unit on thermal chemistry, and then we actually balance the heat. Okay? But in this case, we just need to balance the reaction. Now, let me give you a hint. What are you going to balance last? You save that oxygen for last, because if you change that, that doesn't screw up anything else. You always balance the oxygen last. Okay? So, ramen, I got 4 carbons. So what am I going to do?
I have two.
What?
I don't know, I heard somebody say two.
I got 4 carbons here.
Yeah.
So how am I going to get 4 carbons on my product side? Put a 2?
Oh, 4. Yeah.
How about a 4?
Yeah.
Okay, is that good?
Wait. 5.
Yes, it's.
Well, okay, now I know. I was looking at it weird. I didn't see the other. Okay,
Good.
you could go up.
Okay. Okay. I got 10 hydrogens. Ramen.
Oh my gosh. Okay.
How am I going to get 10 hydrogens on the other side?
Put 5.
There you go. Okay, that's good. Now, I've got 8 oxygens here, right? And I got 5 oxygens there. So I have 13. Oh, that's tough. Okay, it's tough. Because if I put a 6 there, I have 12. If I put a 7 there, I get 14. So how many do I need? 6.5. But I can't have half of an oxygen. So what do I do at this point?
Everything by 2.
Well, change this to an improper fraction. So what 6 halves is an improper fraction?
13 over 2.
13 over 2. Then what do I do? Multiply by 2. Then what do? Multiply by 2. So this becomes 2, this becomes 13, this becomes 8, that becomes 10. Now, is everything still balanced?
No.
Okay. How many carbons do I have over there? 8. How many do I have over here? 8. That's kind of cool. Now, I've got 20 hydrogens over here. I've got 20 hydrogens over here. I've got 16 plus 10. I got 26 oxygens over here. 13 times 2. I got 26 oxygens over there. It's balanced.
Ew, I don't like that. Please don't put that on our test.
What are the odds you're going to have a problem like that on the test?
50%. 100%.
100.
100. Hunskies. Guarantee you. Guarantee you. When you hand in this test, if you haven't done one like this where you have to multiply the coefficients by 2 to get rid of a fraction, you have done something wrong. Okay? Now, if you notice, it's good if mathematically it happens when you have a number of hydrogens that's 10, but when you divide by 2, you get an odd number. So like when you had 5, that got me that 5 oxygens there. So that's kind of an indicator of that's what's going to happen. So I promise you, if you get done and you hand in this test and you have not cleared out the coefficients by multiplying by 2, you have done something wrong. Okay? I'm going to tell you straight up.
Well done.
Tell you straight up. Okay. Now, let's talk about number 22.
Come on, give me that back.
Now, what I'm going to do is wrong.
You're so wrong.
Okay? I have fluorine plus magnesium chloride, and that's going to get me magnesium fluoride and chlorine gas.
Oh.
Boo! Is horrible. Why? Why? Is there anything right with what I did?
It needs to be MgCl2.
Why?
Because magnesium has a charge of 2 plus and chlorine or chloride only has 1 minus.
Okay, so that needs to be 2. First off, why is this reaction even going to take place? Where's fluorine in relation to chlorine? It's above it, so that means it's more reactive. Fluorine comes along, it's like the spicy, hot senior. It comes up to the freshman and goes, "Yo, mind if I dance at your date?" The freshman goes, "Here, I'm out." Senior's more reactive. Okay, so
That's illegal.
now what? Is it still right?
There needs to be 2 with the F.
There needs to be 2 F's. Why?
Because it's diatomic.
Because it's diatomic.
Yeah.
Okay,
On both
cool.
sides. On both sides, yeah.
On both sides?
Uh-huh.
Now,
Put it
is this F2 because it's diatomic?
No,
Or is this F2 because of the magnesium?
Magnesium.
because it's magnesium.
Okay, because the magnesium has a charge of 2 plus. Now am I done?
No, you
Why?
need to put a 2 in front of the Cl on the right.
No, I don't. No, I don't. No, I don't. No, I don't. No, I don't.
Subscript 2.
I need to put a subscript 2.
Oh, because it's a diatomic.
Chlorine's one of the diatomics.
Okay.
This is not a golf ball, this is a...
Hey, I did it.
Okay. Any other ones you want me to go over?
Can we go over 27, please?
Yeah.
Oh yeah, 27.
Yeah.
So here's the story.
He's saying no to you.
So all combustion reactions release energy, right? That's the point. This is why if it's cold over the weekend, you go, "Hey, let's light a fire in the fireplace," right? Let go. Leave the golf ball alone. Leave the golf ball alone.
We're playing soccer.
Stop.
Okay.
I realize that. I promise you I'm not going to ask you anything on the World Cup on the test on Monday.
Oh, dang.
Okay? So why do you burn wood? What are you hoping to get out of it? You're cold. What are you trying to get released from that? Heat energy, right? So remember, just go back to any decomposition reaction. Any decomposition reactions, you put heat into it to break bonds, right? So heat flows in and you break bonds. Think of melting ice, okay? So if you put energy in to break bonds, then when you form bonds, then what's going to happen?
Please.
You're going to release energy. Okay? So when you form new bonds, you release energy. You put energy in, you break them, you form new bonds, you release energy. Okay? That's it. So when you look on that question, it says heat is a product. Is more energy put in to break the bonds, or is more energy released in the formation of the bonds? Because heat is an overall product, that means you're going to release more energy in forming the new bonds than you do in breaking the bonds.
Okay.
Okay? 29, one substance will gain electrons, and the one that gains electrons is the one that is reduced. So both of your answers to 29 is gain. Leo says go. Lose electrons, that's oxidation. Gain electrons, it's reduction. So Leo says go. Leo, go. Okay? Any other ones at all you want me to go over that you think you might have a question on? Raman, is that yay, nay, good, we're solid?
Wait, no. Can you do 19?
I can do
I
that.
did it for you, Mr.
Okay, so I will do it under one condition. First off, you tell me what type of reaction 19 is.
Double.
Okay. So, you have sodium phosphate, Na3PO4, true?
Mm-hmm.
And then you've got iron 3 chloride, FeCl3, true?
Yeah.
Okay. So what are you going to get out of this?
Sodium chloride.
Sodium chloride, cool.
Iron phosphate.
And what?
And iron phosphate.
So how are you going to write your iron phosphate?
FePO43.
FePO4,
No.
no.
Wait, let me think.
Okay, I got time. What charge is the iron over here?
3.
3 plus. What charge is that phosphate?
3.
3 minus, right? So how am I going to write iron 3 phosphate?
Keep it.
Keep it like you have it.
Keep it like it's FePO4?
Yeah, that's what I said.
Yeah. So what do you need to do? How are you going to balance it?
Put a 3 in front of the NaCl. Is that it? How
So-
did I do it wrong?
Now, let me give you a hint. And this typically happens on double displacement reactions. If you get a situation where you cannot get it to balance, okay, like you're going back and forth and back and forth and back and forth and back and forth, and you can never get it to balance, odds are you wrote one of the formulas wrong, okay? So if you cannot get a double displacement reaction to balance, regroup, go back, check your oxidation states, okay? Make sure that you wrote the chemical formula correctly, okay? Make sure that you can do that. In terms of decomposition reactions, okay? The only ones I'm really going to expect you to know that what you're going to get is this, is that there's 2 of them, okay? Just because these are the most often. So for example, on number 5, okay, you have magnesium chlorate, MgClO3, 2. So I'm going to expect you to know that chlorates decompose into metallic chlorides and oxygen. Okay? If this had been potassium chlorate, we would get potassium chloride and oxygen. If it was sodium chlorate, we'd get sodium chloride and oxygen. So just remember chlorates, okay, give you oxygen because they have a lot of oxygens out there that go off by themselves, and you have the chloride left over. The other one that I'm going to expect you to know is one like number 9, where you have magnesium carbonates, and you get the oxide and carbon dioxide. So those are the 2 I'm going to expect you to know. And if you just think about it, they're fairly self-evident. Chlorates, you have lots of oxygens. Carbonates, you get that, and here's the reason why, and I'm going to tell you how this is going to play out. If you produce oxygen, and I might say, hey, you're going to heat up 2 different substances in a test tube. You put a burning wood splint in one of them and it goes out. You put a burning wood splint in another one and it glows brighter. And I'll ask you, which one is the chlorate? Which one is the carbonate? And then I'm going to say, hey, write and balance that decomposition reaction. Okay? So, chlorates, you get metallic oxides. Carbonates, you get carbon dioxide. And how you can tell that is the reaction, how they react with the burning wood splint. Okay, any other ones at all you might have a question on? Yes, Grace?
Number 28, I think you might have said something about it, but I don't know what I was supposed to write.
Okay. So here's the deal. So let's say that you're at a dance, okay? So here's couple number 1, here's couple number 2, right? What's the only way that they could switch partners? What physically has to happen? If they're locked in together, could they ever switch places? No. They can only switch places if you break the bonds that hold them together. Because if they're locked up, we can't switch places, right? So so in double displacement reactions, we have to have ions that are floating around, like iron and nitrate, and then sodium and carbonates, okay? I have to have those in solution so that they can recombine. If they're locked up as solids, nothing can happen. So we have to have them as aqueous solutions so that they're moving around and then recombine. Okay? Does that make sense? Okay. Anything else? By the way, let me give you a hint on number 15. You should have 2 silver nitrates if you balance that correctly. On number 19, you should have 3 sodium chlorides if you do that one right. On number 14, you should have 2 silver nitrates if you do that one right. On number 7, you should end up with 9 oxygen molecules if you do that one right. On number 7, you should have 9 oxygen molecules if you do that one right. Okay? I promise you there's going to be net ionic equations. Okay, I promise you, I promise you, I promise you. Now, if you want to hold on to this green sheet and hand it in on Monday and use this as the basis for the test, that's cool. If you're done with it, if that's up to you. Now, here's what I'm going to give you for the test. Okay? So, I'm going to give you this piece of paper, the Rock and Rowdy review for the equations test. And on all of these, for the first 22, all I've given you is the reactants, like magnesium chlorate. That's it. Hydrochloric acid and calcium hydroxide. That's it. Okay? C4H10 plus O2. Okay? All of these things. Now, on some of these, like for example, on number 11, you have potassium oxide and water. So the other thing about decomposition reactions is that you should be able to reverse the process. Okay? So if, for example, chlorates yields chlorides and oxygens, so if you reverse the process and you take oxygen with the chlorides, you're going to recombine them into the chlorates. So synthesis and decomposition reactions are offered like mirror images of each other. So if you decompose it into a certain set of products, if you reverse it and take those products, you'd recombine them into that product. Okay? So then you got some questions, and then 28 is nothing but net ionic equations. So if you want to get, and then the other thing I'm going to do is I'm going to give you this, I'm going to give you the answer key so you know exactly what you've done right and what you've done wrong. Okay? So on the test, keep in mind, I'm going to give you this. Okay? You will have this available to you on the test. You're going to have a periodic table available to you on the test. Okay? That's what you're going to have. So if I were you all, this is what I would do. I would take this and I would treat it as the test. I wouldn't even look at that answer key. I wouldn't breathe on it. I would just hide it. Okay, put it away. And I'd go through and I'd take that reactivity chart. I'd take the solubility rules, and I'd take your knowledge, and I would try and do this. Okay? Because here's the problem. As soon as you look at mine, you have instantly biased yourself in terms of how what's going to happen. Okay? So what I would do, I would hide that answer key, put it away, didn't even look at it. I would go completely through this test, and I would try and work it start to finish. Then I basically use that as an answer key, and then I'd go back and go, hey, let me check how I did. Or if you don't know how, let's say you have one and you have no idea how to even start it, okay? Then I'd cover up everything else on that test or on that answer key until I kind of saw what was written down, and then if you get a hint like, now I know what to do, okay? Just a word of advice, okay? That is, because here's the worst thing that you can do. is look at my answer key and go, oh, that's exactly how I would have worked the problem. Oh, Burkamp, you're on fire. Man, you're doing good work on this, okay? Bad. Stop. Don't. You have everything back to you. You have all the labs, you have all the assignments, you have everything back to you. Preparing for this test is an active process. What does not count as an active process is you taking a worksheet that I've given back to you and you just read through it. Oh yeah, I remember that. Flip that over. And the parental units come up, what are you doing? Oh, I'm studying for my chemistry test. But no, you're not. You're not actively studying for chemistry tests. You are looking over old documents, okay? What I would do, if you have missed, this is what I would do if I was preparing for this test. I would go through everything. And anything that I had missed, I would work over again, okay? It's like, oh, I obviously didn't know what was going on. I got to figure out what I did wrong, okay? And then I'd work that again and again and again until it just becomes old hat, okay? So the only thing you're really going to have to memorize is the decomposition of chlorates, decomposition of carbonates. You get oxygen, you get carbon dioxide. What are the two products that come out of any combustion reaction?
Water and carbon dioxide.
Water and carbon dioxide. Welcome to global warming. Okay, so here we go. So stop you on the camera.